For this week's problem, Kristen, Serenity, Uma, and Dawson will be walking through it. We're given that a flow is induced by a sliding plate, similar to the setup given in 1007-1014 PowerPoint on page 11. Here, the upper plate is moving with a constant velocity and the flow is steady. No slip boundary condition holds on both of the plates, and there is no pressure difference between the left and the right side of the plate, and the plates are sufficiently large. The fluid inside the channel is an incompressible power law fluid with an apparent viscosity given. The first part of the question asks if the fluid is Newtonian, shear thinning, or shear thickening when n is greater than 0. For this, we said that the fluid is shear thickening when n is greater than 0. This is because the fluid shear rate increasing will cause an increase in apparent viscosity.
So we're trying to use the conservation of mass to determine that the velocity is only a function of y. And so we take a control volume, and using the conservation of mass, we know that rho vx in respect to x is equal to the rho vx in respect to x plus delta x. And because this is an incompressible fluid, we know that the volumetric flow rate in is equal to the volumetric flow rate out. This is delta x, this is delta y. And so we're going to apply the continuity equation that we found in class for the incompressible fluid, which is delta equals 0. And expanding that, we know we get the partial Vx over partial x plus partial Vy, partial y plus partial Vz, partial z equals 0. Because this is 2D, there's no z direction, and we know that the velocity in the y direction is 0. So that means partial Vx over partial x equals 0. And that it is only depending on the y direction.
So we want to determine the shear stress at any point of the fluid, and to do that we need to use Newton's law of viscosity, which is shear stress equal to viscosity times the shear rate. We were given an apparent viscosity, so you can substitute that in, and we know that the shear rate is dvx over dy. So you should get shear stress equals to mu naught times dvx over dy squared, and this is simply because we're setting n equal to 2 as instructed. It's easier to solve that way. If you had left it as n, it makes the problem needlessly difficult. So you want this in terms of, well, Vx, or you just want to get rid of the differential. So you can divide by mu naught to move that over. Then you can take the cubic root on both sides. now this is separable, so you can move the dy over onto the other side, and then take the integral of both sides. Again, we're looking for shear stress, so you can move everything over to the other side. And to do that, you should cube everything first. Should end up getting shear stress equals dx cubed over y cubed times mu naught. This isn't the final answer though, because dx and y are, they can change. And we were given v and h in the problem, so we want to use the terms we were given. And so, oh yeah, and don't forget, like I did, that you would have an unknown constant, because we didn't have any boundary set for the integral. So in the end, you should have v cubed over h cubed times mu naught plus c2, which is again an unknown constant, and that is what your shear stress would be at any point of the fluid.
So for question number 4, we want to determine the velocity at any point in the fluid. So in question number 3, we solved for this equation for tau, and then basically we're going to rearrange that. So what we're going to have to start out is Vx at y is equal to 0 is equal to tau yx over mu naught to the 1/3 power plus c2. This is times y as well. So we're going to use this boundary condition at y equals 0. We also know that the velocity is equal to 0, and that you can see that over there. That's just what a no-slope boundary condition is. So we know that this term goes out to 0, that term goes to 0. So we know c2, our constant from integration earlier, that is equal to 0. And again, we're gonna use the boundary condition mu naught to the 1/3 power times h, because y is equal to h, so you can see how I substituted that in. Then there's no c2, and we know that is equal to v, because the velocity at the top of the plate, the velocity of the fluid at the top of the plate is equal to the velocity of the top of the plate. So that's, Vx is equal to v when y equals h. So what we do here is we have this, and what we do is we solve for tau yx over mu naught, because we can use this. So we'll get v over h to the 3rd power is equal to tau yx over mu naught. And we also know that tau yx over mu naught is equal to dvx dy. So all three of these are equal. So we set these two equal to each other, and then solve for Vx, because that's what we want, the velocity at any point in the fluid. So we solve this equation for Vx. So what we'll end up getting is V over h cubed dy is equal to dvx. And then as we did before, we just take the integral. And then what we'll end up getting is V over h cubed times y is equal to Vx. And that is your velocity at any point in the fluid.